Hello, thank you for joining the Texas Instruments new product update webinar. Just a reminder that this is a weekly series every Thursday at 10 a.m. Central. A few quick announcements before we get started. This webinar will be recorded and available online at ti.com/MPU. All phone lines will be muted, so if you have questions, please use the chat box and we will try to answer in real time, or you can contact your TI salesperson or field application engineer. Today's topic is learn about TI's power density ICs for space grade power management. I will now pass it over to Kenneth Matthews for introductions.
Thanks, Kelly. Hi, everyone. My name is Kenny Matthews. I'm product marketing engineer for the Space Power Group at Texas Instruments, and our group, our product line focuses exclusively on radiation-hardened and radiation-tolerant power management components. So for today, what we'll go through is just running through a quick agenda, talk about our space-grade product flows, a little background on the different product grades that TI offers in terms of power management ICs, and then we'll really focus on two key elements of our portfolio, which is our buck converter overview, and then our LDOs, linear regulators, as well as a DDR termination regulator. Really, this is geared for full power solution on powering a lot of different FPGAs, but this also works for a number of different processors, as well as custom ASICs you may be designing. So with that, we'll talk about space power trends. So historically, the classic radiation levels is 100K rad, 75 MeV for designing long-term geosynchronous satellites. But with the advent of new or decreasing launch costs, there's been certainly a downward pricing vector happening on satellites. So there's a cost element that's becoming more stringent on a lot of these satellites. The other vector that we've been looking at, certainly as many of you know, is a trend for more increased onboard processing. So what this is meaning is this is more computing on a satellite. These are kind of turning into higher grade, increasing power demands for FPGAs. And so we'll discuss today on how TI's portfolio of power management ICs can help design with better power density, better efficiency, how that can help you in your design. So with this, TI really offers two types of product grades. On the right here is our rad-hard hermetic. Then on the left here is the rad-tolerant plastic. In the middle, this is rad-hard plastic. This is recently ratified by the DLA back in November. We'll certainly have a lot more products coming in the near future that follow this kind of grade. However, for today, I'll be discussing mainly rad-hard hermetic and rad-tolerant plastic devices. So your rad-hard hermetic devices are your typical Class B, geared for the strictest of radiation environments or reliability levels for satellites. This follows the MILPERF 38535 spec, so it has a lot of different types of qualifications. We'll touch a little bit on that in the next slide. On the left here, this is really the rad-tolerant plastic, or what we refer to at TI as space-enhanced plastic, referred to as space EP. We typically characterize these devices to a lower radiation level. So this is 30 to 50K rad for TID performance. Typically, we do have an RLAT as well, 20, 30, or 50K rad. And then for single event latch up, we do a 43 MeV characterization for SEE rather than the typical 75 you'll see for our rad-hard hermetic devices. And really, what this is geared for is low Earth orbit, some mid-Earth orbit type of satellites or constellation satellites. This offers a more cost-effective alternative rather than trying to use a lot of the rad-hard hermetic devices. So again, with a decreasing launch cost, with the tighter spaces, this is certainly a viable solution from both a cost and board space perspective. And so really, there's this is the difference between the flows identified. Rad-hard hermetic, you can kind of see here, follows the MILPERF 38535 spec. The key differences between the SCP flow and the -SP or rad-hard flow is that we do not do burn-in on our SCP devices, so there's no production burn-in, as well as we don't do live test per wafer lot. Because these are plastic packages, we do an outgassing spec tested per ASTM E595, which is required to pass that. And as mentioned before, we do an RLAT as well on the SCP flow. So again, for the strictness of radiation and reliability environments, you can position the -SP or rad-hard Class B devices for something that needed for a more cost-effective solution on LEO and NEO type of applications. You can look to leverage the SCP devices. So that what we're discussing today is really offering a full space-grade power management solution. So we have a number of devices in our portfolio that are able to power auxiliary rails, lower power rails, a number of LDOs for noise-sensitive rails, DDR termination regulators if you have DDR memory on a number of different type of payload cards, and as well as both high current and low current solutions. There are a number of resources that we'll talk about that you can use to leverage, but all of the devices that we'll be talking about today are released on TI.com. And as standard for all our products, you'll find that we'll have radiation reports, TID, SEE, and NDD reports, as well as EVMs and design tools like models, both transient and for our rad-hard portfolio, WCA models to help you in your design cycle. So kind of narrowing down on the radiation qualified switching regulators, this is kind of our full portfolio of devices today. And really what this can kind of be broken down to is high current devices and low current devices. So today we'll be talking about 50601, 4002, 4001, and 3, which is both a rad-hard -SP as well as its rad-tolerant 50K rad 43 MeV counterpart in a plastic package, and then the very wide VN switching regulator, the 4010, for again an SCP. So really the key benefits that when looking at our buck converters can kind of fall into these key categories. As mentioned before, you can kind of look at it between high current devices and low current devices. But what a lot of these do is provide best in class power density. You'll find that with the hermetic devices, as well as that even further exemplified in the plastic counterparts. A lot of our devices are stackable or parallelable. We'll talk a little bit about that. Then we'll go into a little detail on, the flow-through layout or the ease of layout that we have with a lot of our devices. So by best-in-class power density, this kind of gives you an overview of the different sizes of what we're referring to. So on the left here is what we have in our rad-hard hermetic devices for switching regulators. The 50601A and the TPS7H4002 are both in the same footprint, same package. So these are respectively the 6 amp device and 3 amp device. One common theme with our rad-hard portfolio is that you'll find that we only have leads on 2 sides, a 2-side leaded package. So rather than having leads on 4 sides, this helps further decrease your footprint application. So giving you even more benefits when comparing to other competitors in the market in terms of a footprint power density size. In comparison here, and this is just TI portfolio of what I'm showing here, for easy math, we're using just a 1 V out at maximum current. So this kind of shows you a milliwatt per millimeter squared in terms of power density and really how that scales across our portfolio. So for the lower current devices, you'll find that this is the highest power density ICs in the market today, including the 7H4001, which is more so the higher current device. So this is our 18 amp, more so geared for the core rails of a lot of these FPGAs. As you can kind of see here, the maximum current or the maximum power density here increases due to the higher current. And again, this is the highest power density IC for core rails, high current applications in the market. And this is further expanded, as you can kind of see here, with our plastic portfolio offerings. Now, these are at lower radiation levels, but again, in the theme of power density, we're trying to give you better performance, smaller ICs, to really have an impact on your size, weight, and power. So that we'll talk a little bit about the evolution of core power rails. As mentioned earlier, there's been more demand and more need in the market for onboard processing. And as a result, there are many of these FPGAs that are used in satellites and payload cards that are requiring and demanding more power. This is primarily generated or taken from the need for the core rail. The core rail is a lot of where that power is requiring. You kind of see here just the evolution of some of the FPGAs in the market. 10 amps for the RTG4, KU60s, maximum 36. Even with the new Versal, we're seeing max current of 150 amps. So again, we'll talk a little bit about how you can leverage a lot of our devices in our portfolio to scale for these higher currents. So really, in order to achieve higher currents, it's fairly simple. We try to make it very, very easy. Both are in our hermetic portfolio, both the 4001 and low current offerings, 50601A and 4002, are able to be paralleled. With the high current offerings, you're able to parallel 4 of these devices without any type of external clocking needed. So that's up to 72 amps. And it's 4003, or plastic counterpart is able to do the same. They're very, very similar devices. Looking at the low current devices, you're able to do this. It has similar architecture, but these are, again, more so geared for the auxiliary rails, really to achieve the higher current rails, specifically on something like the KU60, or perhaps even the Polar Fire. The 4001 or 4003 would be best positioned. So what you're essentially able to do, and you can find the data sheet online, certainly this will have more information, but you'll essentially just tie the same pins together, fairly simple, and this will be essentially 90 degrees interleaved, or 9 degrees out of phase to each device. So 4 devices, 72 amps, total current rating, each channel 90 degrees out of phase. So that another common thing with our switching regulators is their ease of layout, or what we'd like to talk about is design with flow-through in mind. So essentially with buck converters, there's 2 noisy loops that are created by the high switching current, one during the on time, one during the off time. And being able to essentially have your outputs grouped together, power nodes grouped together, this gives you an ideal layout LC filter. So there's a lot of things here that terms from a noise performance, as well as a layout. It makes it easier for a layout on the design end. You want to keep these loops as small as possible to avoid high losses in noise, and these smaller loops are able to minimize switching noise and parasitics that might be impacting your design. Being able to essentially have these grouped together and not spread out across the package, right, is really the key implement on, one, creating a smaller footprint, overall footprint size for you, the designer, as well as making it easier in terms of a layout perspective. So you'll find that a lot of our devices, and this is just the 4001 as an example, but you'll find that a lot of our devices tend to group a lot of the noise generating rails. It's really just a lot of the power pins. And then we try to isolate as much as possible the very sensitive pins. Of course, this is, in terms of layout, you'll want to try to isolate this even further, how you're implementing your design. But from a package and pin-out standpoint, you'll find that these are useful and helpful when designing. So with that, we'll touch on some of our space qualified linear regulators. So everything I talked to just a second ago about our high switching or buck converters, all of those are released devices, been out in the market for at least a little while. Everything in red today is fully released, but I also want to talk about two new devices that we just recently put on TI.com. So these have early prototypes available right now with release to market or final production flight units in early to mid-July. But today, what we'll focus on is our product offerings for noise-sensitive rails, as well as the DDR termination regulator. So really, there's kind of three categories that I'd like to discuss. One is on existing solutions. So this will be general purpose as well as a high current LDO. And then we'll talk about a little more in terms of a performance standpoint. If you're looking for something with very, very high PSRR, very, very low noise, we'll certainly touch on our new device that we released, as well as a repackage of our hermetic 3302 into a plastic SEP flow. So really, in terms of existing solutions for noise-sensitive rails, we have three options to powering a lot of the, whether it's ADCs, DACs, or really geared for the noise-sensitive rails on FPGAs. For our rad-tolerant plastic, we have this 73801. This is more of a general-purpose LDO. So really, where it shines is small form factor, 6.5 by 3.5 millimeters, as well as a very, very wide input voltage range. It goes from 2.2 volts to 20 volts, current rating of a 1 amp. So you'll find in a lot of our block diagrams, as well as some of the resources that I'll touch on at the end here, anything geared for a SEP grade or rad-tolerant LDO, you'll be able to use the 73801. We'll have a new product offering, the 7H1111, that I'll talk about later. Kind of in the same spirit, the 7A4501 is a general purpose, another general purpose LDO. However, this is a rad-hard version. So this is a QMLB ceramic hermetic device. Again, fairly small form factor is what we're going for, 7 by 7.2 millimeters. Another very, very wide input voltage range, LDO, 2.3 volts to 20 volts. And then you can kind of see the current rating here. And this is both a QMLB as well as RHA device. And then our last device in our linear regulator portfolio that you're able to leverage is the TPS 7H1101A. So this device is a high current LDO. Kind of see here up to 3 amps. This is our highest current LDO in the portfolio today. Larger package than its general purpose counterpart, but the idea here is that there's a lot of integrated features with this specific LDO as well. So you have enable, configurable soft start, and power good for sequencing applications, as well as an integrated protection feature called current fallback protection. So again, if you're looking for, depending on your needs, small form factor, wide input voltage, you can kind of leverage our general purpose LDOs, or if you're looking for something that's more of a higher current with more integrated features, you can certainly look to leverage the 7H1101A. We'll talk a little bit about the performance in just a second. So first, we'll touch on the DDR termination regulator. So this is one of our new releases, the 7H3302. So if you're powering the need, or you're powering DDR 1 through 4, you might be needing some type of termination regulator that has the capability to both source and sync current. So 3301-SP is the rad-hard hermetic device, been in the market for a while now, but we are repackaging this into a plastic SEP flow. So this is a radiation-tolerant 3 amp sourcing DDR termination regulator. The plastic package will give you a size benefit, as well as a more cost-effective solution for LEO or MEO type applications. The design benefits here, again, this is more so a compact power solution, so you won't need an inductor or external compensation that you might typically see with a switching regulator. This is a linear device, so very, very few passes are required. And as mentioned before, this just kind of goes into a little more detail of its capability to both source and sink current. Then lastly, I'll touch on the noise-sensitive application LDO. So this is our brand new, what we're referring to as RF LDO. Again, this is a 7VN 1.5 amp device. However, this will be the highest PSRR, lowest noise LDO currently available on the market, space-grade LDO. This both comes in a rad-hard as well as rad-tolerant space grade of options. So this is TPS 7H1111-SEP, as well as a TPS 7H1111-SP. So as mentioned before, this is really good for use cases on low noise or high PSRR, a very, very good companion part when trying to power ADCs, DACs, any type of phase lock loop implementations, any type of cleaning up of clock jitter on, phase noise jitter on clocks. And really, I think the best slide that kind of showcases this is this. So this is a comparison of what we have in terms of our current LDO offerings. So you kind of see what I mentioned earlier about the 7A4501 and 1101A. Already touched a little bit on that. The 7H1111, this RF device, or excuse me, RF LDO, is the line in blue here. And essentially, this is measured data comparing what we have available today. So you can kind of see already the significant performance increase that we have on 7H1111. So really where the 1111 starts having some significant impact is on the higher frequency range here that you'll see in a lot of the, to eliminate a lot of the harmonics that will be coming from switching regulators. So even at 1 megahertz, you're still getting about 70 dB of performance. A substantial improvement from our other LDOs in the market. Similar, you'll find that the 7H1111 has very, very low output noise in comparison to the 1101A as well as the 7A4501. This is even, even taking a look at the 1/F noise, which is fairly it's unfeasible to try to filter out using passives. This will really, really help in a lot of powering clock applications where phase noise will be extremely important. So as a result, by using the 1111, this not only provides a high performance or higher performance LDO that you're able to leverage, but really also, again, it's a power density move that helps eliminate the need for excess LC filters or PI filters. So a lot today, you'll see a lot of switching noise coming from your DC-DC converter, plus their harmonics. And to achieve a similar performance or something that's comparable to the 07H1111, you likely need to have an LDO plus an LC filter with a ferrite bead into some noise-sensitive application. A lot of the LDOs today, at least looking at our devices, have a severe or a far further dropout when it comes to a lot of the higher frequency range for PSRR. And this is where the 7H1111 will be able to help eliminate the need for a lot of LC filters or PI filters, saving you, the designer, a lot of board space. The second thing to kind of look at is certainly it'll help increase or help with your transient response, any type of load step function, whether it's from an off state to an on state or from a low power state to a high power state. With passives, there's certainly probably a less than ideal transient response. By using the 1111, you'll have something more ideal there. So you can kind of find both this 3302, the DDR termination regulator, as well as the two 1111 devices, both available on TI.com today. There's a data sheet, there's EDMs available, and as mentioned earlier, we'll see final release of production devices early to mid-July. So with that being said, to kind of look and start evaluating some of your devices, please look and leverage the TI Space Products Guide. This will give you a good overview of a full portfolio of TI devices, not just power, but DACs, clocks, anything in terms of analog need for power, for space applications. For more information regarding the SCP flow, more details discussing mold compound, the change in bond wires that we use, single control baseline, and you can kind of use this to get more details on the SCP flow. And then for a full, a deeper discussion and the technical analysis of some of the power management solutions that we have for the Xilinx FPGAs or RTG4, you can use these two application notes and white papers to get you started in your design. Thank you all for coming, and this concludes my presentation.
Great, thank you, Kenny. And thank you everyone for attending today's NPU webinar. The recording and PDF version of the slides will be available at ti.com/NPU. See you next week for our next topic, reduce system design efforts with flexible RS-485 transceiver THVD 1424. Thank you everyone and have a great day.